Hi, I'm Will Thomason. I'm presenting Task and Motion Informed Trees, or TMIT-Star, an efficient, almost surely asymptotically optimal integrated task and motion planner. This is joint work with Marlon Strub and Jonathan Gamble. Integrated Task and Motion Planning, or TAMP, is a family of approaches to solving long-horizon robot planning problems that combine logical and physical constraints from high-level specifications. For example, here, the robot is tasked with sorting the sticks by color, specified by the environment geometries and a high-level goal statement. Typically, TAMP solvers holistically combine a symbolic planner to choose what actions to take, with a continuous or motion planner to decide how to carry out the chosen actions. TMIT-Star is an efficient TAMP solver that, given additional computational time, is able to improve solution costs. It almost surely converges asymptotically to optimal solutions. For our purposes, optimality refers to the sum of the piecewise path length of the robot's motion in the solution, but it's important to note that TMIT-Star is agnostic to the particular cost function chosen. Here, we see the PR2 carrying out a solution to an instance of the clutter clearing problem, in which it must move the sticks from their original positions to one of two tables according to their color. At a high level, TMIT-Star iteratively interleaves relaxed symbolic planning with asymptotically optimal multimodal motion planning to find solutions to task and motion planning problems. It begins from a symbolic action model and problem description, as well as geometry models for the environment, robot, and movable objects. TMIT-Star first formulates and solves a relaxed version of the given symbolic planning problem. This relaxation optimistically elides constraints in the symbolic planning model that have a defined geometric interpretation, which leaves behind only the purely discrete parts of the problem. This relaxation defers consideration of geometric constraints to the motion planner and simplifies the symbolic planning problem. TMIT-Star then solves this relaxed problem with a novel satisfaction modulo theories, or SMT, based planner that enforces symbolic constraints as needed and incrementally finds make-span optimal, meaning as short as possible, symbolic plans. Once TMIT-Star has found a candidate symbolic plan, it attempts to find valid motions and continuous action parameters, such as grasps, to carry out the plan. TMIT-Star models this search as batch sampling-based motion planning in a multimodal configuration space. A multimodal configuration space, for our purposes, can be thought of as a collection of copies of the joint robot and object configuration spaces. Each copy, or mode, corresponds to a different value of the purely discrete symbolic state of the problem. Thus, a candidate symbolic plan induces a sequence of mode transitions leading from the starting mode to the goal mode. TMIT-Star samples batches of states in each mode along the sequence, moving between modes at transition states from which the corresponding actions in the symbolic plan can be used. Finding the necessary transition states can be challenging. This corresponds to solving the geometric constraints that TMIT-Star elided earlier in the symbolic planning stage. Further, many transition state manifolds, such as object placement positions, grasps, etc., will be naively sampled with probability 0, and not all transition states on a transition state manifold are geometrically feasible or valid. TMIT-Star solves this problem by projecting uniform random states from its batch of samples onto the transition state manifolds if and only if they are within a distance threshold of the manifold. This effectively inflates the transition manifolds to positive measure in the configuration space and avoids wasted computation by only attempting to sample a transition if TMIT-Star has a reasonable initial guess. We call this just-in-time action grounding. Given batches of states in the relevant modes, TMIT-Star uses the asymmetric bidirectional search of the AIT-Star asymptotically optimal motion planner to efficiently find a motion plan from the start state to the goal. We benefit from AIT-Star's reverse search, which skips edge validation and allows us to identify likely feasible paths before putting in the effort to fully validate them. Edge validation happens during AIT-Star's forward search, which typically needs to expand far fewer edges. Further, because AIT-Star is an almost surely asymptotically optimal motion planner, we're able to improve the solution cost given additional computational time, both within each mode, improving the length of motions, and across modes by finding new symbolic plans that admit better corresponding motion plans. If any stage of this process fails, we generate appropriate blocking constraints to add to the symbolic planning problem and iterate to find a new plan candidate. Our results show that TMIT-Star can solve problems that require manipulating many objects. Here we see a solution to an instance of the clutter clearing problem. And the same instance, given additional computational time to improve solution cost. TMIT-Star can also solve geometrically constrained problems, such as the shelf manipulation problem shown now. In this problem, the PR2 must swap the blue and green sticks. Again, given additional computational time, TMIT-Star can improve upon the quality of its initial solution. In comparison to earlier work, we show that TMIT-Star has a significant performance advantage, and we further validate that TMIT-Star is capable of converging toward optimal plans given additional computational time. Thank you very much for your attention. To learn more, please check this page for our paper and code release, and feel free to get in touch.